you know that that's going to go away, that's going to go away, that's going to go away, and that's going to go away, right? So the only ones you have to worry about are the first two. Every time I take a derivative, every time you take a derivative of something that's a power function, what happens to the power? The power drops to the front, and it reduces by 1, right? So if you do it once, let's just do first derivative. F prime is going to be 2 times 7 times x to the 6 minus 4 times 6 times x to the 5th, right? So that's the first. Now you just have to keep track of it. Now here's the thing. If you take, what's the second derivative of x squared? What's the second derivative of x squared? What's the second derivative of x squared? 2. It's just 2, right? 2x and then 2, right? What's the third derivative of x cubed? What's the third derivative of x cubed? Do it in your head. What's the third derivative of x cubed? 6. 6. Because x cubed goes to 3x squared goes to 3 times 2 times x goes to what? 3 times 2, which is 6, right? But you'll notice, what is 3 times 2? That's also 3 factorial. You drop down all of them. The point is it's a constant. If you take the nth derivative of something to the nth power, you will get a constant. The x power will go away. I'm just trying to give you the generality. So you can keep on doing this. You could keep on doing this piece by piece. What is it? 2 times 6 times 7 times x to the what? 5th minus 4 times 6 times 5 times x to the 4th, right? So then you can do it again. And it's helpful to do this out. So what is it? 2 times 7 times 6 times 5 times x to the what? Minus 4 times 6 times 5 times 4 times x to the what? So if you keep on doing this to the 6th derivative, it's going to end up being 4 times what? 6 factorial, right? And then what's this one going to be? The 6th derivative is going to be 2 times 7 times 6 times 5 times 4 times 3 times 2. Let's see, that was the first derivative, second derivative, third, fourth, fifth, sixth times x right there. That's it. There it is. It's actually, that is what I'd want to see right there. Do you notice how I did not multiply it out at the beginning? Why didn't I multiply it out at the beginning? Is there any point to multiplying 2 times 7 times 6 out at the beginning? No. Why is it really important for me to see this in your work? Yeah, I can see if it's a factorial or not. It also shows me if you did it properly. You know, like for example, 2 times 7 times 6 is something I would look for, but do I have any idea off the top of my head, like 2 times, like, oh yeah, 7 times 6 is 42, 84, you know, but then all of a sudden it gets really big, right? Like, can I recognize visually 2 times 7 times 6 times 5 as being the proper work? Yes. Do I know off the top of my head what 2 times 7 times 6 times 5 actually is? No, I don't. So basically, it's kind of like when you have polynomials, don't multiply them out unless you have to. Do you remember that rule? Like, don't multiply things out unless you have to? Well, I'm telling you now, don't multiply things out unless you have to. That would be a perfectly acceptable answer right there.
We can write it as a factorial.
Yes, you could. So you could say f6x is equal to 2 times 7 factorial x minus 4 times 6 factorial. Maybe use judicious use of parentheses. Because it's not 2 times 6 and like not 12 factorial. That's a lot bigger. Factorial is a very big function. It gets big fast. And it comes up all over the place. Okay, any others from the homework? What is that? That's the second derivative, and then you set it equal to 0, and you get x equals 4/3. What do you have to test at that point, though? What do you have to test to see if it's an inflection point? So the work right here doesn't actually test it. The work here finds the y value. You see this? The work here is they put this into the original function to find the y value. That's great. That's the point. But did this test to see if it is an inflection point? You need to test it. So what do you need to make? You need to make a line, right? So you do a line like this. You have 4/3, and this is the x value and the double prime value like this. And I'm not going to do it. We can do it out. This is where it's nice to have you could use a calculator, but you can also just carefully choose your values here. What's the original function? F of x, what is, the second derivative is easy on this one. This one's totally easy. It's negative 6x plus 8 is the second derivative. What's a really nice number like to the right of 4/3? Well, no, to the right. 2? Plug in 2, what do you get? Is it negative or positive? It's negative, right? What's to the left of 4/3? Or better than that? 0. Always go to 0 if you can, okay? Sometimes 0 breaks things because you can't divide by it, but go to 0. And what is it? Positive. So it goes from concave up to? So is this an inflection point? You have to test it, you have to test it, you have to test it. That will hit you in the face sometimes because you will get questions where like, what's the inflection point? You're like, oh, it's fourth. No, it's not. It doesn't have any inflection points because it doesn't change concavity. It's a false flag. Oh, you can't even see that. You're like, blank screen? On number 1, have we ever done a derivative like that before? Take a look at number 1, everybody. Hands up, heads up. Put your, you don't need to write anything down.
Yes.
Have you done a derivative of that before? Really? 2 to the x. Ah, so what is it? Anybody remember? What is f prime of x going to be? ln a times a to the x. Now that is something you just get to use. We don't prove it. You just get to use it, right? So what is, if g of x is 7 to the x, what's g prime of x? ln 7 times 7 to the x. Nice. So excellent. So therefore, what would be, let's go the other direction, what would be the integral? What would be the integral of a to the x? What would be the integral of a to the x? The derivative of what is a to the x? Well, that's the derivative of the derivative. So what's the integral? It's going to be a to the x, but what's going to be in front of it? Careful. Yeah, you do. Yeah, you do. The derivative of what is a to the x? You can do it.
A over ln a.
Oh, you're so close. Why? It's a to the x over, you were so close, ln a. Like that. Because what is, again, if you don't look at this, what's the derivative of a to the x? ln a to the x. But what do you want to get rid of? The ln a, because it's not there. So what is this actually? It equals this right here, plus c. Nice. So let's take a look at this.
Isn't what Arvin said right if you multiply it out?
I'm sorry, say that again?
Can't you write it out as a...
Yeah, you could write it as a to the x over ln a. Yeah, you could write it like that, sure. I like this just because it follows a pattern. This over here, so what's the integral of e to the x? 1 over ln e times what? But what is ln e? 1. So this is just 1 over 1 e to the x plus c. Yeah, you're right, but you are right. What about this one right here?
Wait, so that's weird. E to the x, the integer, and the...
Bingo. The integral and the derivative. What's the derivative of e to the x? E to the x. What's the integral of e to the x? E to the x. Cool, huh? That's a big one.
Plus c.
I kind of ran right over. And plus c if you do the integral, yes. Plus c. What about this one right here? What's this one going to be? What can you do with the 5? What are you allowed to do with this 5?
5 over ln e.
You're just allowed to pull it out to the front. So we now know what's the integral of e to the x? E to the x. So what's the integral of this going to be? 5 times e to the x plus? That's it. The 5 is just along for the ride. Let's go to this one. What can we factor out to the front here? 7. So what does this one become?
1 over ln 4.
7 times 1 over
ln 4
times
4 to the x.
4 to the x plus e. Do you see those parentheses I put in there? Those are super important. Please put them in. You will mess this up if you don't. What about this one? Can someone just do this one for me? Who thinks they can safely navigate this one for me? Who can do it? Arvin, go. What is it?
1/2 x to the, or 1/3 x to the third.
Yes.
Plus 0.
Mm-hmm. 0? You sure?
5.
We're not taking the derivative. We're taking the integral. So what's it going to be? Anybody want to help him out?
Pi squared times x.
Yes. Pi squared times x. Yep.
And then
Plus what?
1 over ln 5 to the x.
Yes. Plus? Perfect. Yeah, pi squared is just a number, right? What's the integral of a number? Oh, wait, the number times x. Yay! Super exciting. Super exciting. Nice. Okay. So, let's try this one right here. Find the exact area between the curve 2x minus 2 to the x minus 4 from x equals 0 to x equals 6. Try that by yourself. No calculator because you want it to be exact. No calculator. Try that for me right now. See if you can do that. And what does this turn into?
1 over ln 2
Yep.
times 2 to the x minus 4x.
1 over ln 2 times 2 to the x minus what?
4x.
And you're integrating that. You're doing that from what to what?
0 to 6.
0 to 6. Plug in 6. So what do you get? 2 to the 6 over ln 2 minus 24. And then what are you subtracting? This is important. What are you subtracting now?
0.
2 to the 0. No, it's 2 to the 0 over ln 2 minus 0. What is 2 to the 0? What's 2 to the 0? 1. So what do you have here? 2 to the 6th over ln2 minus 24 minus what? 1 over ln2. So the final answer would be this. Now, if you wanted to simplify that, I would simplify it like this. 2 to the 6th minus 1 over ln2 minus 24. That would be your final answer right there. That would be a great way to write your final answer. How do you feel about this one, everybody? Pretty good? Pretty good? Okay.